Today we're going to take a look at section 10.1, which is plane curves and parametric equations. So as we start taking a look at this, just kind of to develop the idea of what's happening here, I've written a little bit for us to think about. So we will often find it convenient to describe what x and or y is doing in the plane by using a specific kind of parameter. The parameter that we're often going to use is the letter t. And t often, in context, if we're working with something that has a context to it, is representing time. So for instance, if you had a moving object, you would naturally give its location in terms of the time. That is, when it is at a specific location, when it is at the value specifically for x, and when it is a value specifically for y. So we can talk about x and y in terms of t, the time, and we can define two equations, x of t and y of t, which are parametric equations. So what we're going to be working with is we're going to be working with equations that look like we've got a system of equations, two equations instead, and seeing how those interact with each other to actually give us one graph, not two. And I hope that you have your calculators with you today because we are going to talk about that in a little bit. That's our second example. Let me show you the first example, and then we'll talk in terms of the first example about how that plays into being able to use your calculator to help you with the second one. So just to get right off started here, we're going to sketch a plane curve. It's defined by the given parametric equation, so we're always going to be working with two equations, x and t. I'm sorry, x in terms of t and y in terms of t. And we're going to draw this equation on an xy plane. So one of the things you might automatically recognize is there's no t-axis, right? So I don't have anything called t on my graph, but I'm going to draw an xy plane. And what we're going to do is we're going to make a table of values. That's what we're really going to do over here. So again, if you have your calculator out, it might be helpful to just calculate these quickly. For the sake of what we're doing here, you can write these for the moment, and I'll show you how to use your calculator a little differently in a second here. But just for using what your calculator says right now, just put this first one in as y1, the second one in as y2, and you can put the t in as x. Okay, that's going to allow us to generate our table fairly quickly, and then I'll show you how we can do this once we change our calculator settings in a moment. And because we're working with sine and cosine, it will be nice to use t values that are helpful to be used with sine and cosine. Things like what? I don't think 1's going to work very nicely. Pi might work real nice. Pi over 2. So think in terms of trig, right? Some of you I had in trig. So when we're looking at values for these things in trig, so we've got a table here, it's got t in it. I'm going to have an x in it, I'm going to have a y in it. And my t values are going to sort of oscillate around what we do when we're doing trig. So I'm going to start with 0. What would occur most naturally in the unit circle that gives us nice cosine and sine values? Pi over 2, exactly. Pi over 2 is a helpful value. What's next? Pi. What's after pi? 3 pi over 2. And then 2 pi, and that actually puts us back where we were when we were at 0, because these are cyclic functions, right? Whatever we got on the first line, we should be getting on the last line. So take your calculator. If you put in these equations into y1 and y2, you're going to put in, then, for the x values, these specific t values we just wrote down. All right, so when t equals 0, what does the first equation give you? Right here. What do you get? 1 plus 2 cosine 0. What is that? It's 3. Thank you, Jordan. 3. What do you get for y? What is negative 2 plus 2 sine of 0? Just plugging in the values. Make sure you're in radian mode as you're working with this. It shouldn't affect anything at the moment, but it will shortly if you're not. What is it? Negative 2 would be correct. Okay, does everybody get both of those values so far? Excellent. What happens when we put in pi over 2? What do you get for the first equation if you put in pi over 2? 1. Good. Now you guys are all got your calculators going. How about the second one?
0.
0 is correct. What about when you put in pi?
Negative 1.
Negative 1. And when you do the second equation?
Negative 2.
I got negative 4. Does anybody else get negative 2? Maybe I've got mine.
-4 I get for 3 pi over 2.
Oh, sorry, you're right. I'm on the wrong line. You're right. So this one's negative 2. This one was negative 4. Thank you. And then what about 3 pi over 2 for the x value, the first equation? 1. Okay. And we have one more at pi over 2, or at 2 pi, excuse me.
3.
We should be back to 3 and negative 2. So we are back where we started, right? So if we continue, and we continue using pi over 2 increments, this is going to successively get us the next value that's going to be just the same value you already had, right? You guys with me? I'm just going to repeat my values again. So we're going to come over here to the xy plane, and we're going to graph these points. Everything is pretty small values. So 4 away is sufficient, so I'm going to go with 4. All right, the first point is at 3, negative 2. The second point is at 1, 0. I probably should use another color. The third point is at negative 1, negative 2. Then I have 1, negative 4. Then I'm back to 3, 2. So I've got 4 purple dots on my screen right now. Now we chose these particular y or t values because they were convenient to plug values into, right? Yeah, I mean that's why we picked them, is because they were nice to use. But of course we could have picked values in between. We could have even picked values that aren't terribly horrible between, like pi over 4 or pi over 3 or something like that. What is the shape going to be if I connect the dots appropriately? It's a circle. It's going to be a circle. And if you weren't sure, yeah, it doesn't look much like a circle. I'm not a very good artist. It does look like a circle if you connect it in a smooth way. Yeah. And if you weren't for sure, you could try one of the values in between, like pi over 4, pi over 3, and get an approximation, because it'll change you'll have to change the radicals into an approximation to be able to graph the dots. This is a circle. One of the things that we're going to have to plot when we do this, though, is we're going to have to plot the direction that we plotted our points. So all of these are going to have a direction on them, and the direction in which I plotted my points looks something like this, right? I started at the 3, 3, negative 2, and I moved around the circle, in this case counterclockwise. So all of your curves are going to have a direction arrows on them. So this is interesting because you probably didn't look at this and say, you know what, I bet this will be a circle when I'm done, did you? No. And we know it's going to stay in a circle, and it's going to keep going around the circle because the sine and the cosine values are going to keep giving us the same xy pair as we go, right? It's going to be cyclic. All right, so there's one other piece of of directions that we haven't done. This says to sketch the plane curve, which we did. And then it says to find an xy equation for the curve. Now, in general, when you are finding an equation and trying to eliminate something, you could solve one equation for t and plug it into the other one. That's not especially helpful on this set of equations. Why? Why would that not be friendly? Sorry, I didn't mean to just change the screen. Yeah, like the inverse, right? We'd have to do an inverse sine or an inverse cosine. And that's going to be kind of ugly looking, and then we're going to have to do some sort of something with a triangle and simplify. So for this particular one, that's not a very helpful approach because we're looking at t's that are inside of an angle. They are an angle inside of a sine or a cosine. So as you're working on some of your problems, that's a very good approach. It just doesn't work very well for this one. So we're going to do something a little bit different, and I'm going to give you a suggestion. So let me write these two lines or two equations on the second slide. All right, so as I'm looking at these, there's some things that I'm sort of noting in my brain. So I'm going to say this out loud so that you can say, yep, I see that too. All right? So one of the things that I'm noting is that I've got a sine and a cosine in them. And you have some trig identities that relate sine and cosine together. Tell me some trig identity that you know that relates them together. Yeah, and that's a really helpful one, because if I had sine squared and cosine squared and I could replace them with the number 1, t would go away, right? So that's a really handy identity, and that's actually the one we're going to use here. So good job, James. Yes. So that's what I'm going to think about. Now, the problem here looking at this is that I don't have them squared, right? So what would I need to do to get them to be squared? Yeah, square both sides of the equation. Now think with me for a moment. There's a problem if I do that the way that the equations are currently written. What's the problem? Yeah, these pieces would end up having to make me FOIL something, right? Which would mean I'd still have sines and cosines left. Are you guys with me? Are we tracking on that? So just squaring them as they are is not going to be a good approach. However, if I move them and then square them like you're suggesting, then I won't have that problem. So far, so good? So the first thing I'm going to do is I'm going to take each equation and I'm going to get the sine and the cosine to be alone. And there's really no reason to move the two. That doesn't affect anything in terms of squaring because it's multiplication. All right, so the next thing we're going to do is exactly what our goal was to be able to do here is I'm going to square both sides. Okay, everybody good so far? I don't really need to distribute the squaring out on the left because actually if I leave it there, you're going to see something a little bit nicer than if I were to simplify it. So I'm going to leave this as squared on the left. And then on the right, we're going to see the pieces actually give me 4 as coefficients, and then sine squared on one of them and cosine squared on the other one. So if I'm wanting the sine squared and the cosine squared to go away, they're going to have to be inside of the same equation. And right now they're two separate equations, right? So how could we get them so that they're inside of the same equation? And that's exactly what we're going to do. We're going to add the equations together. So this sort of looks like a glorified arithmetic problem from like 2nd or 3rd grade, right? We're going to add the pieces on the left. So I'm going to have x minus 1 squared plus y plus 2 squared. And on the right, I'm going to have 4 cosine squared of t plus 4 sine squared of t. And we did that because I actually can factor the 4 out now. I have that sine squared plus that 4 cosine squared. So what am I left with on the right? This is 4. Now take a look at the equation that resulted. It is a circle with a radius of? No, 2. Radius of 2. With a center where?
-1, 2.
Close. 1, -2. You have to do the opposite. All right, so the center is the opposite sign, so it's 1, -2, and the radius is 2. Does that match your picture?
Yes.
Does your picture have a center at 1, -2? Not if you connected it, right? All right, so there's my center, roughly, anyway. I'm at 1, -2, and I have a radius of 2. So that's cool, right? We were able to eliminate the parameter. Here's the nice thing about what we did. A circle in an xy equation, like the one we got over here, is not a function. Why not?
Two values for one.
Yeah, for every x value in the xy plane, I have 2 y values. Or you might have been thinking, in fact, some of your drawing lines in the air, I can see you doing it. Vertical, yeah. It does not pass the vertical line test, those sorts of things. But in parametric form, it's 2 functions, isn't it? That's really helpful because there are some things we can do with functions that we can't do something not a function. So it's a very helpful feature in this particular situation. I want to show you, since we've got this and we're about to do a problem that's going to require, not require, but ask you to do it this way anyway. Grab your calculator out. And I can tell you how to do this on the 83s and 84s, but I suspect it's very similar on the 89s, so if you have that with you, that's fine. We're going to learn how to graph parametric equations on here. How's that sound? All right. Hit the button that says mode. You're going to change that to parametric. Man, you guys are sharp today. All right, go on down there. The first one says function. The second one says PAR. It's probably what you see. It's parametric. The third is polar, and then there's SEQ for sequence. We're doing parametrics today, okay? So you're going to put the second one on there, parametric. When you do that, I want you to hit y equals and tell me what you see happen.
Yeah, x1, y1, t.
You have x1, y1 of t. Do you see that? Each of your equations now inside of your calculator has two different, an x equation and a y equation. And hit the x button. What does it say now? It says t. Now, you need to know how to work with this because it doesn't work the same way that it does. So go ahead. We're going to do the one that we just did. The one that we just did had x equals 1 plus 2 cosine t. So 1 plus 2 cosine t.
If we have a T button, should we just use the T button?
I don't know. Give it a try and see what happens. You let us know. Okay. The second one is negative 2 plus 2 sine of t. Before you go and hit graph, unless you already have, okay, I need you to hit window. The window looks different. Tell me some of the things that you see in the window. You got t's in there, which makes sense because you've got this variable t going on right now, right? You've got one that says t min, one that says t max, and one that says t step. Everybody see that? We're going to manipulate with those first. When we created our table a moment ago, what was the minimum t value we used? 0. So let's let t minimum be 0. What was the t max that we used? 2 pi. So let's put 2 pi in there. And what was the increments by which we stepped? It was pi over 2. Now we need to be careful because if we enter pi over 2, I suspect that the calculator probably will draw us a parallelogram. And we know that's not really what we want to happen, right? It generated a nice table of values for us, and we sort of interpreted that it's probably not really going to be that. Yeah. So let's let our... Did you see your parallelogram there, James? Isn't that wonderful? So we want to be a little bit careful. Even if our table is going by increments, we may want our increments to be something smaller. And it doesn't have to be in terms of pi, but I'm just going to put mine in terms of 0.1. Okay, so it's just going to increment slowly. I mean, it's going from 0 to about 6.28, and it's going to do it by 0.1s. Now, if you put it too small, it's going to take your graph a long time to graph. And so you don't want the the t values increment that it's stepping to be too small. So you don't want to spend forever watching the thing graph. Well, I mean, there's always that. All right, your x min, your x max, your y min, your y max. That's your choice. So we tend to use that negative 10 to 10 kind of window. We know this graph is actually going to be perfectly fine if we did like negative 5 to 5. So if you want to do that, that's fine, or negative 4 to 4, but negative 10 to 10 is fine as well. After you get those in there for your x and your y, and then the scale for that being 1 is good because that means you see all the hash marks at 1 unit's a part of everything. Hit graph. And it looks like an oval. Do you know why it looks like an oval, Joel? Yeah, because your screen is actually a rectangle, right? It's actually a longer screen, wider screen than it is tall. So that's why it's looking like an oval instead of it looking like an actual circle. But as long as you're seeing where your coordinates are, you should recognize that even though it looks like an oval, it's really a circle. Wow, we could do that. Let's do zoom trig. So zoom 7 is what mine is. Hang on, I didn't do something right. I didn't. Oh, mine did turn into a beautiful circle. You're right. Zoom trig was very nice. So if we're working with sine and cosine, that would be handy. Okay, everybody good?
I'm on left graph. I think it's my calculator.
Huh, let me take a look.
Oh, it's still an oval. It's just the other way now.
Yeah, that's what
But
mine
if I
is.
get that, but if you go to the second table, you get all the values. Zoom squared. Let's try that one. I think that works.
I did decimal pretty good.
Hey, Caleb, do zoom squared.
Okay, you guys ready for another one? The next one that we're going to do is completely in your calculator, so how cool is that? Okay, you've got a couple of them on your homework that are going to be like that. So here's an example. Use a graphing calculator to sketch the plane curves defined by the parametric equations. There's no sines and cosines here, so probably zoom trig's not going to be helpful. But we can change our y and our x to be these particular equations. So we've got t cubed minus 2t, and then t squared minus 3. And you can manipulate your window. It's probably still going to be somewhat similar to what we had before in terms of your t-step.
Mine didn't
did you see something different? This isn't a circle, right? That shouldn't surprise you that it's not a circle. What's it look like? Can't honestly tell. Kind of like a lot of talking. Okay. Yeah. So if you turn your head sideways and you sort of finished out the picture that seems to be missing, what would it look like? It looks a little bit like a parabola. I want you to change something so you can see that it probably actually looks a little bit more like it than you were expecting. Hit window. And let's make your T minimum something negative. Give me an example. We already have our maximum in there if you haven't changed it as 2 pi. Not that that's particularly special, but let's make it the equivalent. Okay? So why don't we make our T max and our T min equivalent but opposite values? So something like maybe -2 to 2 or -5 to 5 or something like that. Now what happened? How cool is that? That was unexpected, right? We thought maybe you'd finish out something down here and it didn't do that. I just made mine -2 to 2. It'll probably show a little bit. Mine just cut it off. Make it -5 to 5 is probably better. Yeah. Meters looks really good. You got it. So isn't that a cool graph? Now there's nothing special about the fact that when we started before, I started at 0. Okay? The graph that you're seeing right now is a more complete graph. Agreed? So that's the graph we're going to draw. So you're going to have to play with the table values a little bit to figure out what you're seeing in order to see something that's complete. Does that make sense? So there is a little bit of trial and error here with your table. So we're going to sketch something. It is a sketch, but do your best to make it look fairly accurate, of course. And so I think it's crossing on the xy axis at y equal -1 and at y equal -3. Does that want to look like to you guys? So those are the points I'm going to plot here. And it's crossing the x-axis at maybe 2 and -2. How's that look? Can you see it well enough to decide? Maybe somewhere between 1 and 2. I'll put it sort of in between. And then we're supposed to be connecting this the way that it does. Did you see how it connected it? That is, which direction? Because we need direction curves on here, just like those arrows that we done the last one. Where did it start and where did it end? Like, in what direction are we going to put my arrows? Yeah, it actually moved. Did it move from left to right or from right to left? I think it moved from left to right, didn't it? Yeah. Like it started over here, swooping, and then it went back over. Okay, so then my arrows look something like this. Okay, is everybody okay with that one? All right, we're going to go the other direction now. So we've talked about taking something that looks parametric, or is a parametric equation, a set of equations, and turning it into something that is a standard equation. That's what we did over here, right? Our standard XY equation. We're going to go the other direction here. This one we're going to take and we're going to create or find parametric equations that describe the given curve. So the first one that we're going to look at is a portion of a parabola. So this is a portion of a parabola, but it's only between the points 2, -2, and 0, 2. So those are XY pairs of points. Recognize first. So if you take a look, what you're actually seeing is you're seeing the x value there. Here's your y value here. So your x value is sort of going from a +2 to a 0. Your y value is going from a -2 to a +2. Everybody good with the interpretation so far? Thinking about that? Now, in general, when you're creating a parametric equations, if you've already got an equation, like y equals 2 minus x squared, you can simply let x equal t. Now, don't write that down yet because it's not going to work here. Or if you do write it down, make that note to yourself. This doesn't work. And let me tell you why it doesn't work on this one. In general, it's a good place to start. Here's the problem. When we're done with the equation, whenever we get it, we want the t value to go between two sets of values. Well, if I let x equal to t, and x goes from 2 to 0, then that means that t goes from 2 to 0. What's wrong with that? that's not increasing values, right? In other words, right now, I would have to write down, oops, this, based on what I'm doing. That doesn't work. Do you guys see that? So we're going to change the x equals to t into something slightly different. Notice, if the t value were negative, that would fix some of this, right? Yes? No? Maybe? Why is what?
Why can the t not be?
It can be, but the way that we write that we're going to do our t values is we're going to write them in terms of where it starts and where it stops. So t has to start at a smaller value than it stops at. Right? Because our parametric curves start and stop in terms of time. So your time can't be 2 when it starts and 0 when it stops. So we're going to manipulate the equation to fix that. So that's why I'm showing you this right now, is because we need to manipulate the equation. What we're going to do instead, because this doesn't work, is we're going to let x equal to 2 minus t. Now, let me explain the pieces and where they're coming from. I'm doing the negative t because that's going to switch this inequality around and do something that makes sense. Okay? Right? And I'm going to put the 2 in there simply that way that the t starts where? It's going to start at 0 then. Okay? So if t actually is starting, or if x is starting at 2, then t is actually now going to start at 0. And where is it going to end? Two, right. So we're just thinking about taking these numbers right here, not this one, sorry, this one, and evaluating this x equals 2 minus t. So if x is equal to 2, that means t would have been 0. If x is equal to 0, then t would have had to been 2. Okay, so I'm changing this from the values of x as the x coordinates of these 2 points into the values of t. Okay. Do notice the phrase up here says, find parametric equations. Do you notice what it doesn't say? No, well, that's true. It's true, it doesn't say graph it. It doesn't have the word the in here. Any idea why that would be different? Say that louder, Taylor. There's multiple answers. Okay? So the fact that I needed the negative t was simply to change the direction to put the inequality in the right order. The fact that I put the 2 in there was my choice. I put it in there so that my t value would start at 0. That's all. Are you guys with me? It's kind of nice to say that the time starts at 0, especially if we're talking about context of something, right? Time being negative doesn't really work very well in a context kind of a situation. So that's where that 2 is coming from, and that's why it's not absolutely crucial, is because these are parametric equations that work. They're not the only parametric equations that work. Okay, here's the deal now. Now we have x equals 2 minus t, and we have an equation up here in terms of y. So how can I turn y into something in terms of t? Exactly. Plug 2 minus t in for x. Right? I've already defined one of them in terms of t. The other one has an x in it, so I can simply eliminate that x value by writing in what x equals. So I can take this and write this as y equals 2 minus, because that's the 2 minus from up here, and then 2 minus t squared. So take just a moment and simplify that equation for y for me and tell me what you get. What do you have? It is a quadratic equation. Do you have it, Joel? Do you have it written down?
Yeah, but it's backwards. I guess.
That's okay.
T squared minus 4t minus 2 is what I had. I don't know that.
I think it's negative. Is it negative t squared?
No, it's plus. Plus positive t squared minus 4t minus 2.
I think it's negative t squared. Yeah. It's got a negative right here.
Oh, yeah.
So I think we'll get negative t squared. What's next after that? Positive 4t, is that what I heard?
Yeah.
And minus 2? Okay. So I'm going to write over here, after I've done all this sort of work that I've done here, that the parametric equations are x equals, at least a set that works, are x equals 2 minus t, y equals negative t squared plus 4t, whoops, 4t minus 2, and then my t value is going from 0 to 2. I want you to grab your calculator, because your calculator should tell you whether you did it right. Agreed? So take these two parametric equations that you've created and put them into x and y in your calculator. And then in your window, your t value needs to be going from 0 to 2.
Sorry, what did you say to do again? I didn't catch that.
You're going to put these equations in your calculator, 2 minus t, and the y value, the negative 2, t squared plus 4t plus minus 2, excuse me. And you're going to make sure your window goes from 0 to 2, because that's the portion that we're supposed to be looking at, that's supposed to be getting. So does it look parabolic? Does it look like a portion of a parabola? Yep. And does it actually start at the x value 2, y value negative 2, that first point that's listed? And does it end at the x value 0, the y value 2? Does it start and end at the right places?
Yep.
Then you have found a set of parametric equations that works. So if I'm looking at your homework and you create something different than I create, you know the easiest way for me to figure out if you've created something that works? Is to look at a graph, and I can see, and then I can check back on your work if there's an error. But I can see in terms of the calculator whether or not it actually gives me the right shape. Yes, Jordan?
What shape was this?
What's that?
What shape are we looking
It said parabolic in the, in the directions there. It says a portion of a parabola. And if you weren't sure by this portion of it, because I'll tell you what, the portion that you're seeing right now, it isn't like super convincing parabolic, because I only see this small tiny bit of it, right? If you wanted to make sure you're really seeing something that looks like a parabola, you could extend your values of t to see that it looks more parabolic. Now that's not going to be the portion that this is referring to, but it does give you a broader picture of the whole curve, and that would be okay as well. Let's take a look at another one. This one's a little different. Initially, I was just going to do one example with this kind of a direction set, but this next one is a little bit different in how it starts. I still have 2 points, 0, 1 to 3, and 3, 4. I have 2 points. But it's talking about a line segment, and I'm not given an equation. So this looks quite different than the one we were just doing. Agreed? Yeah, I mean, this doesn't quite look the same, because I can't just let something be something and plug it into another equation. I don't have any equations to work with, so what do we do? All right, so if you're working with a line segment, then you're working with segment, your two parametric equations are also going to be lines. Okay? So I want us to first write out two general equations for lines with x and y and the variable t. So my first equation, x, just so that we're all on the same page, I'm going to write x equals at plus b. And for my y, I'm going to write ct plus d. So t is the variable like x normally is when we write our equations of lines. A, b, c, and d are all numbers, and we've got to figure out what they are. So far, so good? All right. Now, again, this is find parametric equations, which means there's more than one way to do this. Agreed? But again, it's very natural for t to start at 0. So I'm going to choose the t values that are most convenient for me because I get to. I get to make that choice, and so do you when it's your turn in your homework. I'm going to choose that the t starts at 0 and it ends at 1. And you can write less than or equal to, since it's actually for the segments that sounds like it's including these endpoints. Segment includes endpoints. So think with me. If t is equal to 0, I can use that inside of these equations along with the fact that the first point when t equals 0 that I should be at is the value 0, 1, and I can use that to find part of these equations. In particular, this says that when t equals to 0, my x value is 0, because that's what this says right here. Right? That tells me that b equals what? equals 0. So I'm part of the way there to finding the equation of that line. I can do the same thing for y. The y value actually, though, is 1. So this is 1 equals c times 0 plus d. So what is d? 1. So at this point now, I'm using the equation x equals at, y equals ct plus 1. How in the world now am I going to find a and c? And use the other one. So what am I going to write down over here for x equals? What's going to go in the places, and what am I going to have? 3 for x and 1 for t. Like I got to pick, so 1's a nice number to pick. Agreed? But if you picked 2 or you picked 3, it wouldn't be wrong. It'd just be another set of parametric equations that would still work. All right, so here I found out now that a is equal to 3, which means one of my parametric equations is going to be x equals 3t. Over here on y, now what? 4 equals c times 1 plus 1. So c equals what? 3. We'll subtract the 1. C equals 3. So what is my equation for y? 3t plus 1. They don't always have the same slope. They did here, but they wouldn't have to. Okay? And my t value is going between 0 and 1. Graph it. Let's see. Did it work? Do I, in fact, end up with a line segment? Do I, in fact, start at 0, 1 and go to 3, 4? Did it work?
0 to 1.
0, 1 is the first point ordered pair that I'm at, and it ends at the point 3, 4. The t is equal to 0 to 1. Is that what you're asking me, Joel? I'm sorry.
Yeah,
Yes.
yeah. But
yes.
I got that too. I
Mm-hmm.
got the points.
Yeah, the t values go between 0 and 1. We picked that. So if you chose something different on a particular problem for some reason, you just need to make sure that your t value did that in your calculator. Okay, any questions? All right.